So here's something worth sitting with for a moment. Right now, wherever you are, you're lying still. Maybe you've got a blanket pulled up. Maybe the room is dark. Maybe there's a little light coming in from somewhere. And you feel perfectly still. But you're not. You're on a planet that's spinning at about 1,000 miles an hour at the equator. That planet is orbiting a star at roughly 67,000 miles an hour. That star is sweeping around the center of a galaxy at nearly 500,000 miles an hour. And that galaxy, our galaxy, the Milky Way, is hurtling through space at something like 1.3 million miles an hour relative to the oldest light in the universe. You feel none of it, not a whisper of motion. And yet everything, absolutely everything, is moving. Everything is flying apart from everything else, and it has been doing so for about 13.8 billion years, give or take. That's cosmology. That's the thing we're going to wander through tonight. Not quickly, not in any rush. Just slowly, the way you'd walk through a museum after hours when nobody's watching, and you can stand in front of whatever catches your eye for as long as you want. Cosmology is the study of the universe as a whole, its origin, its structure, its evolution, and its ultimate fate. And I know that sounds impossibly grand, almost absurdly ambitious. How do you study everything? How do you even begin? But people have been trying for as long as there have been people, and the story of how we got from looking up at the night sky in confusion to actually measuring the age of the universe to within a margin of about 40 million years. That story is one of the most beautiful things humans have ever done. Let's start where it makes sense to start, not with telescopes or equations, but with eyes. Human eyes looking up. For most of human history, cosmology wasn't really separate from mythology or philosophy or religion. The question, what is the universe, was tangled up with who are we, and why are we here, and what do the gods want? And that's completely understandable, right? If you're standing in a field 5,000 years ago, and you look up and see this enormous dome of stars wheeling overhead, you don't have any framework for understanding it as a physical system. You experience it as a mystery, as something numinous. And so every culture built stories around it. But here's what's interesting. Even very early on, some people started noticing patterns. The stars moved, but they moved in regular, predictable ways. The sun rose and set. The moon went through phases on a cycle you could count. Certain bright points of light, what we now call planets, from the Greek word for wanderers, moved differently from the stars. They drifted against the background, sometimes even appearing to reverse direction for a while before continuing on. And once you start noticing patterns like that, once you start tracking them and recording them, you're doing something that starts to look a lot like science. You're observing, you're finding regularities, and you're trying to build a mental model that accounts for what you see. The ancient Babylonians were remarkably good at this. By around 1800 BCE, they had detailed records of planetary movements. They could predict lunar eclipses. They had a base 60 number system, which, by the way, is why we still have 60 seconds in a minute, and 60 minutes in an hour, and 360 degrees in a circle. That's Babylonian math, still embedded in your daily life thousands of years later. But the Babylonians were primarily interested in prediction, not explanation. They wanted to know when the next eclipse would happen, not why eclipses happen. The why. That was more of a Greek obsession. And this is where the story really starts to get interesting for our purposes, because the Greeks were the first people we know of who seriously tried to build geometric mechanical models of the cosmos. Not just stories about gods driving chariots across the sky, but actual physical models where you could say, the Earth is here, and the sun goes around it like this, and the planets move on these particular paths, and here's why it all works. The big name you probably know is Aristotle, around 350 BCE. Aristotle's cosmology was elegant and intuitive and enormously influential, and, as it turned out, almost entirely wrong. But let's give him credit for what he got right first. Aristotle argued that the Earth was a sphere, not flat, not a disk, a sphere. And he had good reasons. He pointed out that when you watch a ship sail away from shore, the hull disappears before the mast, which makes sense if the surface curves. He noted that the Earth's shadow on the moon during a lunar eclipse is always circular, which only works if the Earth is a sphere. He observed that different stars are visible from different latitudes. These are genuinely good arguments. He was right, and he was right for the right reasons. But here's where Aristotle went sideways. And it matters because his wrong ideas dominated Western cosmology for nearly 2,000 years. Aristotle put the Earth at the center of everything. The sun, the moon, the planets, the stars, all of it revolved around the Earth on a series of nested crystalline spheres. The stuff down here on Earth, rocks, water, air, fire, was made of different material than the stuff up there in the heavens. Earthly matter was imperfect, changeable, corruptible. Heavenly matter was perfect, eternal, unchanging. And the natural motion of heavenly bodies was circular, because the circle was the most perfect geometric shape. Now, think about what that framework does. It creates a fundamental division between Earth and sky. It says the physics down here is different from the physics up there, and it locks you into circular motion as the only acceptable kind of movement for anything in the heavens. That's going to cause enormous problems because planets don't actually move in simple circles. They do that wandering thing, that apparent reversal I mentioned. And if you're committed to circles, you have to get very, very creative to explain that. Which brings us to one of the most impressive wrong ideas in the history of science. About 500 years after Aristotle, around 150 CE, a brilliant astronomer and mathematician named Claudius Ptolemy, working in Alexandria in Roman Egypt, published a massive work that we know by its Arabic name, the Almagest. And in it, Ptolemy built the most sophisticated geocentric model of the cosmos ever constructed. He kept the Earth at the center, because that was the accepted framework, but he added an ingenious mechanism to explain planetary motion. Instead of just having planets move in simple circles around the Earth, he had them move in small circles, called epicycles, whose centers themselves moved along larger circles, called deferents, around the Earth. Picture it like a spirograph pattern, if you've ever played with one of those, a wheel rolling around on another wheel. And here's what's remarkable. It worked, not perfectly, but well enough. By adjusting the sizes and speeds of these epicycles, Ptolemy could predict where a planet would be in the sky with reasonable accuracy. Good enough for navigation. Good enough for calendar making. Good enough that nobody had a compelling reason to throw the whole thing out for over 1,000 years. Think about that for a second. A wrong model, built on a wrong assumption, that the Earth is the center of everything, but engineered with enough mathematical cleverness that it could actually make useful predictions. That's a really important lesson about how science works. And honestly, about how engineering works too. A model doesn't have to be true to be useful. A map doesn't have to be the territory to help you find your way. Ptolemy's system was a beautiful, intricate, wrong map that got people where they needed to go for 14 centuries. But it was always a little bit clunky. It kept needing adjustments. As observations got more precise, you had to add more epicycles, tweak the parameters, introduce little fudge factors. There's a famous claim, probably exaggerated, but it captures the spirit, that by the late Middle Ages, the Ptolemaic system required something like 80 different circles to account for the motion of just 7 celestial bodies. It was getting unwieldy. It still worked, technically, but it was starting to feel like a machine with too many parts. A Rube Goldberg contraption that did the job, but couldn't possibly be how the universe actually operated. And here's the thing about overly complicated models. They tend to be fragile. They work within the range of data you've already seen, but they break down when you push them. They don't generalize well, and they don't give you any insight into what's actually happening. Ptolemy's epicycles could tell you where Mars would appear next month, but they couldn't tell you why Mars moved the way it did. The model was all mechanism and no understanding. So the stage was set, slowly, over centuries, for someone to come along and say, what if we've got the whole thing backwards? What if the Earth isn't at the center? What if the Earth moves? Now, this idea wasn't entirely new. A Greek astronomer named Aristarchus of Samos had proposed a sun-centered model way back around 270 BCE, nearly 2,000 years before Copernicus. Aristarchus suggested that the Earth rotated on its axis and orbited the Sun. And he was right. But almost nobody took him seriously, partly because the idea seemed to contradict common sense. You don't feel the Earth moving after all. And partly because of a technical objection that was actually quite reasonable. If the Earth orbits the Sun, then as it moves from one side of its orbit to the other, the nearby stars should appear to shift position slightly against the background of more distant stars. This effect is called stellar parallax, and Aristarchus couldn't detect it. Nobody could, because the stars are so incredibly far away that the parallax shift is tiny, far too small to measure with the naked eye or any instrument available in the ancient world. Stellar parallax wasn't actually measured until 1838 by Friedrich Bessel. So Aristarchus was right, but he couldn't prove it, and the absence of observable parallax was taken as evidence that the Earth must be standing still. So the geocentric model persisted. Through the fall of Rome, through the long centuries of the early Middle Ages in Europe, through the flourishing of Islamic astronomy. And we should pause here for a moment, because Islamic astronomers made enormous contributions that often get overlooked. Scholars like al-Battani in the 9th and 10th centuries refined Ptolemy's measurements significantly. Al-Tusi in the 13th century developed a mathematical device called the Tusi couple that could produce linear motion from combinations of circular motion, a genuinely brilliant piece of geometry that may have influenced Copernicus centuries later, though the exact chain of transmission is debated. These weren't just people preserving Greek knowledge. They were extending it, questioning it, improving it. But the fundamental framework, Earth at the center, heavens revolving around it, that held. It held because it matched everyday experience, because it had the weight of Aristotle's authority behind it, because it was woven into theological ideas about humanity's special place in creation, and because, honestly, it worked well enough for practical purposes. When something works well enough, people are remarkably reluctant to throw it out, even when it's getting creaky. And then, in 1543, a Polish canon named Nicolaus Copernicus published a book. He'd been working on it for decades, and he was so anxious about the reaction it might provoke that the book, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, was reportedly placed in his hands on the very day he died. Whether that's literally true or a bit of dramatic embellishment, the timing captures something real about how nervous Copernicus was. He knew he was proposing something radical, and what he proposed was, on the surface, simple. Put the sun at the center. Let the Earth be just another planet, orbiting the sun, spinning on its own axis. Suddenly, a lot of things that had required elaborate explanations in the Ptolemaic system became straightforward. The apparent retrograde motion of planets, that weird backward drift, was just a natural consequence of the Earth overtaking a slower outer planet in its orbit, or being overtaken by a faster inner one. It's like when you pass a car on the highway and for a moment it seems to drift backward relative to you, even though it's still moving forward. Same thing. No epicycles needed for that particular puzzle. But here's what's funny, and kind of important. Copernicus's model, in its original form, wasn't actually much simpler than Ptolemy's. Copernicus was still committed to circular orbits, perfect circles, because he hadn't shaken that old Greek assumption. And since planets don't actually move in perfect circles, he still needed epicycles of his own to make the predictions work. His model was arguably more elegant in its basic concept, but in its mathematical details, it wasn't dramatically easier to use. And its predictions weren't significantly more accurate than Ptolemy's updated tables. So why did it matter? Why do we remember Copernicus as a revolutionary? Because he changed the question. He shifted the frame. Once you accept that the Earth moves, once you accept that we're not at the center, everything else starts to shift too. The division between earthly physics and heavenly physics starts to dissolve. If the Earth is just another planet, maybe the same rules apply everywhere. The scale of the universe suddenly gets much bigger. If we can't see stellar parallax, the stars must be unimaginably far away. And the whole philosophical framework that put humanity at the center of a cozy, finite cosmos begins to crack open into something much stranger and much more vast. Copernicus opened a door. He didn't walk all the way through it. He was still too attached to circles, still too cautious in some ways. But the door was open now, and other people were going to walk through it. One of them was a Danish nobleman with a metal nose and an island full of instruments, and another was a quiet, obsessive German mathematician who would spend years wrestling with the orbit of Mars and, in the process, discover something that Aristotle and Ptolemy and even Copernicus had all missed. Something that would turn out to be one of the most fundamental truths about how gravity actually works. Not just here on Earth, but everywhere, across the entire universe. So let's talk about Tycho Brahe first, because honestly, you couldn't make this guy up if you tried. Born in 1546 in what's now southern Sweden, though it was part of Denmark at the time, Tycho came from nobility. He was actually kidnapped as a toddler by his uncle, just taken, and his parents apparently sort of let it happen, because the uncle was wealthy and childless, and it meant young Tycho would inherit well. He was raised to be a lawyer or a statesman, something respectable. But then, when he was about 13, he witnessed a partial solar eclipse, and the fact that someone had predicted it in advance absolutely captivated him. The idea that you could know the sky well enough to say what it would do next, that grabbed him. and never let go. Now, the famous nose. When Tycho was about 20, he got into a duel with another Danish nobleman. The accounts vary on what the argument was about. Some say it was over a mathematical formula, which is just a wonderfully nerdy reason to sword fight. And he lost part of his nose. He wore a prosthetic for the rest of his life, traditionally said to be made of silver and gold, though when his body was exhumed in 2010, chemical analysis suggested it was actually brass, which is somehow even more endearing. But here's the thing about Tycho that really matters for our story. He was, without exaggeration, the greatest naked-eye astronomer who ever lived. And I say naked eye because the telescope hadn't been invented yet. It wouldn't arrive until about 1608, a few years after Tycho's death. Everything he did by staring at the sky with his own eyes and incredibly precise instruments that he designed and built himself. The King of Denmark gave him an entire island, Ven, in the strait between Denmark and Sweden, and Tycho built an observatory there called Uraniborg. It was essentially a castle dedicated to watching the stars, with enormous quadrants and sextants, some of them built into the walls of the building itself, calibrated to a degree of precision that nobody had achieved before. And what Tycho did on that island, night after night, year after year, for about 20 years, was measure. He measured the positions of stars and planets with an accuracy of about 1 to 2 arc minutes. That's roughly 1/30th of a degree. Doesn't sound like much, maybe, but it was 5 to 10 times more precise than anything that had come before. And that precision, that stubbornness about getting the numbers right, is what made everything else possible. Now, Tycho himself had his own model of the solar system, a kind of compromise where the Earth stayed at the center, the Sun orbited the Earth, but all the other planets orbited the Sun. It was geometrically equivalent to the Copernican system in some ways, and it let him avoid the problem of stellar parallax. If the Earth doesn't move, you don't need to explain why you can't see the stars shifting. It was clever, but ultimately it was a dead end. What mattered wasn't Tycho's model. What mattered was his data. Those decades of meticulous observations, especially of Mars, recorded in massive tables that he guarded jealously, because that data was going to end up in the hands of someone who could do something extraordinary with it. Johannes Kepler was born in 1571 in the town of Weil der Stadt in what's now southwestern Germany. And if Tycho's life reads like an adventure novel, duels, islands, royal patronage, Kepler's reads more like a story of dogged persistence against constant misfortune. His family was poor. His father was a mercenary soldier who eventually abandoned the family. His mother would later be accused of witchcraft, and Kepler would spend years defending her in court. He was sickly as a child, with poor eyesight. Ironic, for someone whose work would reshape astronomy. He couldn't have done what Tycho did, couldn't have been the great observer, because he literally couldn't see well enough. But Kepler could think. He could calculate. And he had this deep, almost mystical conviction that the universe was built on mathematical harmony, that God was a geometer, and that the true structure of the cosmos could be discovered through mathematics. Early in his career, he published a book called Mysterium Cosmographicum, The Cosmic Mystery, in which he tried to explain the spacing of the planetary orbits using the 5 Platonic solids nested inside each other. It was beautiful, it was ingenious, and it was completely wrong. But it showed that Kepler was someone who took mathematical structure seriously, someone who wouldn't be satisfied with a model that merely predicted positions but didn't reveal the underlying geometry. In 1600, Kepler went to Prague to work with Tycho, who had by then left Denmark after falling out with the new king and had set up shop as the imperial mathematician to the Holy Roman Emperor Rudolf II. Their relationship was complicated. Tycho recognized Kepler's mathematical brilliance but was reluctant to share his precious data. He doled it out in small pieces, keeping Kepler on a short leash. Kepler was frustrated, ambitious, desperate for access to those Mars observations. Then, in October 1601, Tycho died suddenly, possibly from a bladder infection after refusing to excuse himself from a banquet, though there have been persistent rumors of mercury poisoning. His death was investigated centuries later, and the mercury poisoning theory was largely ruled out, but it gives you a sense of how dramatic this whole story is. What matters is that after Tycho's death, Kepler gained access to the complete observational records, and he set to work on the orbit of Mars, which Tycho had specifically assigned to him. Perhaps because Mars was the most troublesome planet, its orbit deviated most visibly from a perfect circle. Kepler thought it would take him about 8 days to solve. It took him nearly 6 years. Think about that for a second. 6 years of calculation, by hand, no computers, no calculators, just ink and paper, and an almost inhuman tolerance for tedium. He tried everything. He tried different arrangements of circles, different equant points, different combinations of uniform circular motions, and he kept getting close, tantalizingly close, but he couldn't get his predictions to match Tycho's observations. There was always a discrepancy of about 8 arc minutes. 8 arc minutes. That's about a quarter of the apparent width of the full moon. Most astronomers would have shrugged and said that was close enough, that the error was within the noise of the observations. But Kepler knew Tycho's data was accurate to within about 2 arc minutes, which meant those 8 arc minutes of error weren't observational noise. They were real. Something was genuinely wrong with the model. And here's the kicker. Here's the moment that changes everything. Kepler made the extraordinary decision to trust the data over 2,000 years of philosophical assumption. He abandoned circles. He let go of the idea, stretching all the way back to Plato and Aristotle, that celestial motion had to be circular. And he started trying other shapes. He tried ovals. He tried egg shapes. And then, after an agonizing process of trial and error and calculation, he found it. An ellipse. Mars moves in an ellipse, with the sun at one focus. Not at the center, at one focus. And suddenly, everything fit. Tycho's observations matched beautifully, all of them, within the margin of observational error. No epicycles needed, no equants, just a simple, clean, elegant curve. This became Kepler's first law of planetary motion, published in 1609 in his book, Astronomia Nova. Planets move in ellipses with the sun at one focus. His second law came in the same book. A planet sweeps out equal areas in equal times, which means it moves faster when it's closer to the sun and slower when it's farther away. And then, a decade later in 1619, his third law: the square of a planet's orbital period is proportional to the cube of its average distance from the sun. That third law is quietly astonishing. It means there's a precise mathematical relationship linking how far a planet is from the sun to how long its year lasts. Jupiter, Saturn, Mars, Earth, Venus, Mercury, they all obey the same rule. Now, why does this matter for cosmology? Because Kepler's laws did something that no one had managed before. They described the actual motions of the planets with precision and simplicity, without any of the elaborate machinery of epicycles and deference. And they implied something profound. that there was some force, some influence, emanating from the sun that governed how the planets moved. Kepler himself speculated about this. He thought it might be something like magnetism, a kind of sweeping force that pushed the planets along. He was wrong about the mechanism, but he was right that the sun was doing something, exerting some kind of control. The mathematical pattern was too clean, too universal, to be a coincidence. But Kepler couldn't explain why. He could describe the orbits, but he couldn't say what made them elliptical, what made planets speed up and slow down, what the underlying cause was. That question, the why behind Kepler's laws, would hang in the air for nearly 80 years. And answering it would require someone who could unify the physics of earthly things. Falling apples, thrown stones, rolling balls, with the physics of the heavens. Someone who could show that the same force that pulls you toward the ground is the same force that holds the moon in its orbit and bends the path of Mars into that perfect ellipse. That someone was, of course, Isaac Newton. But the story of how Newton got there is stranger and more tangled than the clean version you usually hear, because it involves a plague, a bitter rivalry, and a book that almost didn't get published. So let's talk about that. Isaac Newton was born on Christmas Day, 1642, in Woolsthorpe, a tiny village in Lincolnshire, England. And right away, his life was precarious. He was premature, small enough that his mother reportedly said he could have fit inside a quart mug. His father had died 3 months before he was born. When Isaac was 3, his mother remarried and left him in the care of his grandmother. That abandonment, and it really does seem to have felt like abandonment to young Isaac, left a mark. Newton grew up intense, solitary, suspicious of others, and ferociously private. These personality traits matter for our story, because they shaped not just how he did his work, but how he shared it, or more accurately, how he refused to share it for years. He went to Cambridge in 1661, a quiet, unremarkable student by most accounts. But then something extraordinary happened. In 1665, the Great Plague swept through England, and Cambridge shut down. Newton went home to Woolsthorpe, and over the next 18 months or so, what historians sometimes call his annus mirabilis, his miracle year, though it was really closer to a miracle year and a half, he did some of the most concentrated creative thinking in the history of science. He developed the foundations of calculus. He conducted experiments with prisms that revealed white light is a mixture of colors. And he began thinking seriously about gravity. Now, the apple story. You've heard it. Newton sees an apple fall, has a flash of insight about gravity. And here's the thing. It's actually not entirely made up. Newton himself told this story late in life to multiple people, including his friend William Stukeley, who recorded it. Newton said that while sitting in the garden at Woolsthorpe, he watched an apple fall and began to wonder whether the same force that pulled the apple to the ground might extend much farther, all the way to the moon. The key insight wasn't that things fall down. Everyone knew that. The insight was the question: does this force reach out into space? And if it does, could it be the very thing that keeps the moon circling the Earth instead of flying off in a straight line? Think about what that question means. For 2,000 years, the heavens and the Earth had been treated as fundamentally different realms. Aristotle had said so explicitly. Earthly stuff falls toward the center. Heavenly stuff moves in perfect circles, and those are just different kinds of motion governed by different rules. What Newton was asking, sitting in that garden, was whether that distinction was an illusion, whether the same physics applies everywhere. That's a staggering conceptual leap. But here's where the clean story gets messy. Newton didn't immediately work out the full theory of gravity during the plague years. He made progress, yes. He figured out that if gravity followed an inverse square law, meaning the force gets weaker with the square of the distance, then you could explain why the moon orbits the way it does. But his early calculations didn't quite work out. The numbers were off by enough to bother him. Part of the problem was that he was using an inaccurate value for the radius of the Earth. Part of it was a deeper mathematical question he hadn't yet solved. When you calculate the gravitational pull of a large sphere like the Earth, can you treat all its mass as if it's concentrated at the center? Newton suspected you could, but he couldn't prove it yet. So he set the problem aside, not for weeks, for years, nearly 2 decades in fact, and during those years, Newton did plenty of other things. He became Lucasian Professor of Mathematics at Cambridge. He built the first practical reflecting telescope. He got into a vicious dispute with Robert Hooke over the nature of light. And that dispute matters enormously, because Robert Hooke is the other central character in the story of how Newtonian gravity finally got published. Robert Hooke was brilliant, genuinely brilliant. He was curator of experiments at the Royal Society, which meant it was literally his job to demonstrate new scientific ideas every week. He worked on elasticity, Hooke's law, the one about springs, that's his. He did pioneering microscopy. He contributed to architecture, helping rebuild London after the Great Fire of 1666. But Hooke had a problem. He was a big picture thinker who often sketched out ideas without fully developing them, and then he'd get furious when someone else worked out the details and got the credit. This pattern would define his relationship with Newton. In 1679, Hooke wrote Newton a letter. He wanted to restart their correspondence after years of frosty silence, and he posed a question about planetary motion. Specifically, he asked Newton to think about how an object would move if it were attracted toward a central point by a force that decreased with the square of the distance. Now, this is important. Hooke had independently arrived at the idea of an inverse square law for gravity. He wasn't the only one either. Christopher Wren and Edmund Halley had both been thinking along similar lines. The inverse square relationship was, in a sense, in the air. Several people suspected it was true, but suspecting it and proving it are very different things. Newton didn't reply to Hooke's letter with a full solution. He actually made an error in his initial response about the path a falling object would trace inside the Earth, and Hooke corrected him, which stung Newton's pride badly. But the exchange got Newton thinking about orbital mechanics again, and this time, he had the mathematical tools to go further. He'd spent years developing what we now call calculus, and he'd finally solved that nagging problem about spherical shells. He could prove rigorously that a uniform sphere attracts objects as if all its mass were at its center. With those tools in hand, the problem cracked open. But Newton, being Newton, didn't publish anything. He worked out the key results and put them in a drawer. This is just how he operated. He had an almost pathological reluctance to publish, partly because he hated controversy, partly because he was a perfectionist, and partly because his earlier experience with Hooke over optics had left him deeply wary of exposing his ideas to criticism. So how did the Principia, one of the most important books ever written, actually come into existence? The answer is Edmund Halley. In August 1684, Halley traveled to Cambridge to visit Newton. He had a specific question. Halley, Hooke, and Wren had been debating what kind of orbital path a planet would follow under an inverse square force, and none of them could prove it. So Halley asked Newton directly, if the force of gravity decreased as the square of the distance, what shape would a planet's orbit be? Newton answered immediately, an ellipse. He'd already worked it out. Halley was stunned. He asked to see the proof. Newton rummaged through his papers, couldn't find it, but promised to redo the calculation and send it along. A few months later, he sent Halley a short manuscript, 9 pages, called De Motu Corporum in Gyrum, on the motion of bodies in orbit, and it was extraordinary. In those 9 pages, Newton derived Kepler's laws from first principles using the inverse square law of gravity. He showed why planets move in ellipses, why they sweep out equal areas in equal times, why the period squared distance cubed relationship holds. All of it fell out of a single assumption about how gravity works. Halley immediately recognized what he was looking at. He urged Newton to expand the work into a full book, and Newton, once he got going, became almost manic about it. Over the next 18 months, he worked with an intensity that bordered on self-destruction. He barely ate, barely slept. His assistant later recalled that Newton would sometimes forget whether he'd had dinner. He was building an entirely new framework for understanding motion and force, not just for planets, but for everything. The result was the Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy. And it's hard to overstate what this book accomplished. Published in 1687, it laid out 3 laws of motion and the universal law of gravitation. And then it applied them to an astonishing range of problems: the orbits of planets, the shape of the Earth, the tides, the precession of the equinoxes, the motion of comets, the behavior of pendulums. It was a unified physics of everything that moves, from a cannonball to a comet. But it almost didn't happen. When Hooke learned that Newton was writing the Principia, he demanded credit for the inverse square law. He claimed, not without some justification, that he'd suggested the idea to Newton in that 1679 letter. Newton was so enraged that he threatened to withhold the entire 3rd book of the Principia, which was the part that applied the theory to the real solar system, the part that made the whole thing matter. Halley had to talk him down. He flattered, he cajoled, he soothed Newton's ego. And crucially, Halley paid for the publication out of his own pocket, because the Royal Society had blown its budget on a book about fish. Let that sink in. One of the most important scientific works in human history was almost killed by a priority dispute and was ultimately funded by one man's personal generosity, because the leading scientific institution in England had spent its money on a book about the history of fish. The story of science is never as clean as it looks in retrospect. So what did Newton actually say about gravity? Let's slow down and really sit with this, because the law of universal gravitation is one of those ideas that sounds simple but is actually breathtaking in its implications. Newton said that every object in the universe attracts every other object with a force that depends on 2 things: the masses of the 2 objects and the distance between them. The force is proportional to the product of the masses, so heavier objects pull harder, and inversely proportional to the square of the distance between them. Double the distance, the force drops to 1/4. Triple it, the force drops to 1/9. And here's the word that matters most: universal. This isn't a law about planets. It's not a law about apples. It's a law about everything. The same equation that describes why you stay on the ground describes why Jupiter's moons orbit Jupiter, why comets swing around the sun, why galaxies hold together. One equation, one force, everywhere. Now think about what that means for cosmology. Before Newton, you could describe how planets move. Kepler had done that beautifully, but you couldn't explain why. After Newton, you could. And more than that, you had a tool for predicting things you'd never seen. If you discover a new comet, you can calculate its orbit. If a planet's motion seems slightly off, you can infer that something unseen is pulling on it, which is exactly how Neptune was discovered in 1846, more than a century after Newton's death. But Newton's gravity also raised a profound cosmological puzzle, one that Newton himself recognized and struggled with. If every object in the universe attracts every other object, then why doesn't everything just collapse together into one enormous heap? If gravity is always attractive, never repulsive, and it reaches across all of space, then the universe should be unstable. Stars should fall toward each other. Everything should clump together and collapse into a single point. And Newton knew this. He thought about it carefully, and his answer was essentially a balancing act. He imagined that the universe might be infinite, with stars scattered more or less evenly in every direction, so that the gravitational pull on any given star from one side would be roughly balanced by the pull from the other side. It's a clever idea. If you're surrounded on all sides by an infinite number of stars pulling equally in every direction, maybe the pulls cancel out and everything stays put. It's like standing in the middle of a tug-of-war where every direction has the same number of people pulling. You don't move. But here's the problem with that reasoning, and it's a subtle one. Newton's infinite balanced universe is what physicists call an unstable equilibrium. Think of it like balancing a pencil on its tip. Technically, if the pencil is perfectly vertical and no force disturbs it, it stays balanced. But the tiniest nudge, the slightest breath of air, and it topples. Newton's infinite universe of evenly spaced stars has the same fragility. If any star drifts even slightly closer to its neighbor, the gravitational pull between them increases, which pulls them closer still, which increases the pull further. It's a runaway process. The equilibrium isn't just delicate, it's essentially impossible to maintain. Newton understood this at some level, and in his letters to the theologian Richard Bentley in the 1690s, he essentially admitted that gravity alone couldn't explain why the universe holds together. He invoked God's hand, a divine intervention that set the stars in their places and keeps them from collapsing, which, for a man who had just written the most powerful physics book in history, is a remarkably honest admission of the limits of his own theory. And so this puzzle, Newton's gravitational paradox, just sat there. For more than 2 centuries, it sat there. Astronomers and physicists mostly set it aside and focused on the things Newtonian gravity was spectacularly good at: predicting planetary orbits, calculating tides, understanding the shapes of rotating bodies. The paradox was acknowledged, but not resolved. It became one of those uncomfortable questions that everyone agrees is important, but nobody quite knows what to do with. Now, there's another puzzle from this era that's worth mentioning because it's related and it's wonderfully simple. It's called Olbers's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who stated it clearly in 1823, though others had noticed the same problem earlier. The paradox is this: if the universe is infinite and filled with an infinite number of stars, then no matter which direction you look, your line of sight should eventually land on the surface of a star. Every single line of sight, which means the entire night sky should be blazing with light, as bright as the surface of a star in every direction. The sky should not be dark, but the sky is dark. So something about our assumptions must be wrong. Think about that for a second. It's such a simple observation. The sky is dark at night, and yet it contains within it a profound constraint on the nature of the universe. Either the universe is not infinite, or it's not filled uniformly with stars, or stars haven't been shining forever, or something else is going on that we haven't thought of. Olber's paradox and Newton's gravitational paradox are really two faces of the same deep question. What is the large-scale structure of the universe, and has it always been the way it is now? And for a long time, the prevailing assumption was yes. The universe is static. It's eternal. It's always been roughly the way it is now. Stars are born and die, sure, but the overall arrangement, the cosmic architecture, doesn't change. This was the default view for centuries. Even Einstein held it, right up until the evidence forced him to let it go. But we're getting ahead of ourselves. To understand how these paradoxes finally got resolved, we need to talk about what happened to our understanding of gravity itself. Because Newton's gravity, as powerful as it was, had a crack in it. A small one, almost invisible. But it was there, and one person followed that crack all the way to a revolution. The crack was this: Newton's gravity acts instantaneously. When you move a massive object, according to Newton, every other object in the universe instantly feels the change in gravitational pull. There's no delay, no signal traveling from one place to another. It's as if gravity is a kind of telepathy between masses. They just know immediately where everything else is and how hard to pull. Newton himself was uncomfortable with this. In the Principia, he wrote that the idea of one body acting on another through empty space, without any intermediary, was so great an absurdity that he believed no one who thought carefully about it could accept it. But he didn't have a better mechanism to offer, so he left it. He gave us the math, which worked beautifully, and essentially said, "I'll leave the deeper explanation to future generations." And future generations took their time. It wasn't until the early 20th century that someone finally provided that deeper explanation. And that someone, of course, was Albert Einstein. Now, Einstein's story has been told so many times that it's easy to let it wash over you without really absorbing what he did. So let's slow down and be specific about the problem he was solving, because it connects directly to everything we've been talking about. By the late 1800s, physics had two towering achievements that didn't quite fit together. One was Newton's mechanics and gravity, the framework that described how objects move and how masses attract each other. The other was Maxwell's electromagnetism, the framework that described light, electricity, and magnetism, unified into one beautiful theory by James Clerk Maxwell in the 1860s. Maxwell's equations predicted that light travels at a specific speed, about 300,000 kilometers per second. And here's the crucial thing. The equations didn't say relative to what. They just said light travels at this speed, period. That created a contradiction with Newtonian physics, because in Newton's world, speeds are always relative. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the platform sees the ball moving at 150. Speeds add up. But if you're on that same train and you shine a flashlight forward, does the light travel at 300,000 kilometers per second plus the speed of the train? Maxwell's equations say no. The light just travels at 300,000 kilometers per second, regardless of how fast you're moving when you emit it. That's bizarre. That contradicts everyday intuition. And in 1905, a 26-year-old patent clerk in Bern, Switzerland, decided to take that contradiction seriously instead of trying to explain it away. Einstein's special theory of relativity starts with two postulates. First, The laws of physics are the same for everyone moving at a constant speed. No experiment you can do inside a sealed room will tell you whether you're stationary or moving smoothly. Second, the speed of light is the same for all observers, regardless of their motion. And from just those two ideas, Einstein derived consequences that reshaped our understanding of space and time. Time passes at different rates for observers moving relative to each other. Lengths contract in the direction of motion. Mass and energy are related by the most famous equation in physics, E equals mc squared. Space and time are not separate things. They're woven together into a single fabric called spacetime. But special relativity, as revolutionary as it was, only dealt with objects moving at constant speeds relative to each other. It didn't include gravity. And Einstein knew that was a problem, because gravity is acceleration. When you drop a ball, it accelerates toward the ground. And special relativity had nothing to say about acceleration. So, almost immediately after publishing Special Relativity, Einstein began working on a more general theory, one that would incorporate gravity. And this is where the story gets really remarkable, because it took him 10 years. 10 years of grinding, beautiful, sometimes wrong, sometimes brilliant work. The key insight came to him in 1907, and he later called it the happiest thought of his life. He was sitting in his chair at the patent office. Imagine that. The most important insight in the history of gravity coming to someone sitting at a desk reviewing patent applications. And he imagined a person falling off a roof. And he realized that while you're falling, you don't feel your own weight. You're weightless. If you were in a closed box falling freely, you couldn't tell whether you were falling in a gravitational field or floating in empty space far from any mass. Gravity and acceleration feel identical. They're not just similar. They are, in some deep physical sense, the same thing. This is called the equivalence principle, and it's the foundation of general relativity, and what it led Einstein to, after years of struggle with incredibly difficult mathematics, tensor calculus, Riemannian geometry, tools that most physicists of his day had never even encountered, was a completely new picture of gravity. In Einstein's theory, gravity is not a force that reaches across space and pulls objects together. Gravity is the curvature of space-time itself. Massive objects don't pull on other objects. They warp the fabric of space-time around them, and other objects follow the curves in that warped fabric. The Earth doesn't pull you down. The Earth curves the space-time around it, and you follow that curvature toward the center. Here's an analogy that helps, even though it's not perfect. Imagine a stretched rubber sheet, a trampoline, say, and you place a heavy bowling ball in the middle. The sheet curves downward around the ball. Now roll a marble across the sheet. The marble doesn't travel in a straight line. It curves toward the bowling ball, spiraling inward. It looks like the bowling ball is pulling the marble, but really, the marble is just following the curved surface. That's roughly what Einstein was describing, except instead of a two-dimensional rubber sheet, it's four-dimensional space-time, and instead of a bowling ball, it's any mass or energy. Einstein published his general theory of relativity in November 1915, and it immediately explained something that Newtonian gravity couldn't. For decades, astronomers had known that Mercury's orbit had a slight anomaly. Its elliptical orbit slowly rotates around the Sun, a phenomenon called the precession of the perihelion. Newtonian gravity predicted most of this precession due to the gravitational tugs of other planets, but there was a small leftover amount, about 43 arc seconds per century, that couldn't be accounted for. Astronomers had even hypothesized a hidden planet called Vulcan orbiting close to the Sun to explain it. But when Einstein plugged Mercury's orbit into his new equations, out popped exactly 43 arcseconds per century. No hidden planet needed, just curved spacetime. And then came the dramatic confirmation. Einstein's theory predicted that light itself should be bent by gravity, that a beam of light passing near a massive object should curve because the light is following the warped spacetime. And the amount of bending Einstein predicted was twice what you'd get from a naive Newtonian calculation. This could be tested during a solar eclipse, when the sun's glare is blocked and you can see stars near the sun's edge. In 1919, the British astronomer Arthur Eddington organized 2 expeditions, one to the island of Príncipe off the west coast of Africa, and one to Sobral in northern Brazil, to photograph stars near the sun during the eclipse of May 29th. The results, announced in November 1919, confirmed Einstein's prediction. Light bends by the amount general relativity says it should. The headlines were immediate and global. Einstein became the most famous scientist in the world overnight. But for our story, for the story of cosmology, what matters most is what Einstein did next. Because almost as soon as he had his field equations, he turned them on the biggest question of all. What does general relativity say about the universe as a whole? And the answer he got troubled him deeply, because the answer was that the universe could not stand still. Think about what that means. Einstein had just built the most beautiful, powerful theory of gravity ever conceived, a theory that explained Mercury's orbit, that predicted the bending of starlight, that reimagined the very fabric of space and time. And when he asked it the simplest possible cosmological question, what does the universe look like if it's full of matter, and roughly the same everywhere? The equations answered back with something he wasn't prepared to accept. They said the universe has to be either expanding or contracting. It cannot just sit there. A universe filled with matter, governed by general relativity, is inherently dynamic. It's moving. It's changing. It's alive, in a sense, on the largest possible scale. And Einstein didn't like that one bit. You have to remember the context. This is 1917. Every astronomer, every physicist, every philosopher who had ever thought seriously about the cosmos assumed, deeply, almost unconsciously, that the universe was static, eternal, unchanging in its large-scale structure. Stars might be born and die, sure, but the universe itself, the whole thing, it just was. It had always been. It would always be. This wasn't even really debated. It was more like an axiom, something so obvious it didn't need defending. Newton had assumed it. Everybody assumed it. So when Einstein's own equations told him the universe was dynamic, he didn't say, maybe the universe really is expanding or contracting. He said, in effect, my equations must be missing something. And he added a term, a fudge factor, if you want to be uncharitable about it, though it was mathematically legitimate. He introduced what he called the cosmological constant, a term usually written as the Greek letter lambda, into his field equations. This cosmological constant acted as a kind of repulsive force, a gentle push that could exactly counterbalance the attractive pull of gravity on cosmic scales. With lambda carefully tuned to just the right value, Einstein could construct a model of a universe that was static, finite, and unchanging. A universe that just sat there, perfectly balanced, neither expanding nor contracting. He published this model in 1917, and it was clever. But here's the thing. it was also unstable. Remember how we talked about Newton's problem? How an infinite universe full of evenly distributed matter is like balancing a pencil on its tip. Einstein's static universe had exactly the same issue. If you nudged it even slightly, if one region got a tiny bit denser, or if the expansion rate deviated by the smallest fraction, the whole thing would either start collapsing or start expanding, and the cosmological constant couldn't save it. It was an equilibrium, but a precarious one. A universe balanced on a knife's edge. Einstein knew this, at least to some degree, but he published the model anyway, because a slightly unstable static universe seemed more reasonable to him than a universe that was actively expanding or contracting. That's how powerful the assumption of a static cosmos was. It overrode even Einstein's own trust in his equations. Now, here's where the story gets really interesting, because Einstein wasn't the only person working with these field equations. In 1922, a Russian physicist and mathematician named Alexander Friedmann, sometimes spelled Friedman depending on the transliteration, took Einstein's equations and did something bold. He just let them do what they wanted to do. He didn't insist on a static solution. He explored the full range of possibilities. And what Friedman found was a whole family of solutions, models of the universe that expanded, models that contracted, models that expanded forever, models that expanded and then collapsed back on themselves. The behavior depended on how much matter the universe contained and on the geometry of space itself, whether space was curved like a sphere, or flat like an infinite tabletop, or curved the other way, like a saddle. Friedman's work was brilliant. It was rigorous, and almost nobody paid attention to it. Part of the reason was that Friedman was working in Petrograd. This is revolutionary Russia, the early Soviet period, and communication with Western European scientists was difficult. Part of it was that Friedman was relatively unknown. And part of it, honestly, was Einstein himself. When Einstein first saw Friedman's paper, he thought he'd found a mathematical error and published a note saying so. Friedman wrote back, politely but firmly, showing that there was no error. Einstein eventually retracted his criticism and acknowledged that Friedman's solutions were mathematically correct. But he added, and this is telling, that he didn't think they had any physical significance. Mathematically valid, sure, but not describing the real universe. Friedman died in 1925, at just 37 years old, from typhoid fever he apparently contracted during a balloon flight he'd taken for meteorological research. He never lived to see his solutions vindicated. And that's one of those quietly tragic things about the history of science. Sometimes the person who gets the right answer doesn't live long enough to see the world catch up. But then, independently, someone else arrived at similar conclusions. In 1927, a Belgian physicist and Catholic priest named Georges Lemaitre, and yes, you heard that right, a priest, derived expanding universe solutions from Einstein's field equations and went even further than Friedman. Lemaitre didn't just show that the equations allowed expansion, he proposed that the universe was actually physically expanding, right now. And he connected this theoretical prediction to observational evidence that was starting to trickle in from American observatories. Lemaitre is one of the most fascinating figures in all of cosmology, and he doesn't get nearly enough credit in the popular telling. He'd studied engineering, served as an artillery officer in the Belgian army during World War I, then entered the seminary and was ordained as a priest, and then, because apparently that wasn't enough for one lifetime, he went and got a PhD in physics, studying at Cambridge with Eddington and at MIT. He was deeply devout and deeply rigorous, and he saw no contradiction between those two things. When people later tried to cast his cosmological work as religiously motivated, because an expanding universe that started from a single point sounds a lot like creation, Lemaitre pushed back firmly. He insisted that his physics was physics, not theology, and that the two domains should be kept separate. So Lemaitre publishes his paper in 1927 in a somewhat obscure Belgian journal in French. And once again, almost nobody notices. He actually met Einstein at the Solvay conference that same year and told him about the work. Einstein's response, according to Lemaitre's later recollection, was something like, "Your calculations are correct, but your physics is abominable," which is almost exactly what he'd said about Friedman. The math is fine, but the universe doesn't actually do that. But here's the kicker. The universe does actually do that, and the evidence was being gathered right at that moment on a mountaintop in Southern California. Let's talk about Vesto Slipher for a second, because he's another one of those unsung heroes. Starting around 1912, working at the Lowell Observatory in Flagstaff, Arizona, Slipher began measuring the spectra of what were then called spiral nebulae. Those fuzzy, spiral-shaped patches of light in the sky whose nature was still hotly debated. Were they clouds of gas within our own Milky Way? Or were they entire separate galaxies, vast collections of stars at enormous distances? That question wouldn't be settled until the 1920s, but Slipher was already doing something crucial with their light. When you spread the light from a star or a nebula into a spectrum, a rainbow of colors, you see specific dark lines at particular wavelengths corresponding to the absorption of light by specific chemical elements. Hydrogen absorbs at certain wavelengths, calcium at others, and so on. These patterns are like fingerprints, and Slipher noticed that in many of these spiral nebulae, the fingerprint patterns were shifted. The lines were in the right pattern, but they were all displaced toward the red end of the spectrum. Red shifted. And from basic physics, the Doppler effect, the same principle that makes an ambulance siren sound higher pitched when it's coming toward you, and lower pitched when it's moving away. A red shift means the source is moving away from you. Slipher found that almost all of the spiral nebulae he measured were red-shifted. They were moving away from us. Some of them at enormous velocities, hundreds, even thousands of kilometers per second. And by the early 1920s, he'd measured dozens of them, and the pattern was overwhelming. Almost everything out there was receding. Now, Slipher didn't have the theoretical framework to interpret this as the expansion of the universe. He was an observationalist, a meticulous one, and he reported what he measured. But his data was sitting there, waiting for someone to connect it to the right theory. Enter Edwin Hubble. And this is where the story really comes together, because Hubble provided two things that changed everything. The first was proof that those spiral nebulae were actually separate galaxies, entire island universes far beyond the Milky Way. He did this in 1924 using the 100-inch Hooker telescope at Mount Wilson Observatory above Pasadena, California, which was at that time the largest telescope in the world. Hubble identified individual stars in the Andromeda Nebula, specifically a type of pulsating star called a Cepheid variable, whose intrinsic brightness was known. By comparing how bright the star appeared to how bright it actually was, he could calculate its distance. And the distance was staggering, roughly 900,000 light-years, far beyond the boundaries of the Milky Way. The number was actually an underestimate due to calibration issues that wouldn't be sorted out for decades, but even the underestimate was enough. The spiral nebulae were galaxies. The universe was suddenly, breathtakingly, incomprehensibly larger than anyone had imagined. And then Hubble did the second thing. Working with his assistant Milton Humason, a former mule driver who'd worked his way up from janitor at the observatory to become one of the finest observational astronomers in the world, which is a wonderful story in itself. Hubble combined distance measurements to galaxies with Slipher's redshift data and his own new measurements. And in 1929, he published a paper showing a relationship that would reshape all of cosmology. The farther away a galaxy is, the faster it's moving away from us. Not randomly, proportionally. A galaxy twice as far away is receding twice as fast. 3 times as far, 3 times as fast. A straight line on a graph. Distance proportional to velocity. This is Hubble's law, and it's exactly what you'd expect if the universe itself is expanding. Not because the galaxies are flying through space away from some central explosion, but because space itself is stretching. Every point in the universe is getting farther from every other point, like dots painted on the surface of a balloon that's being inflated. The dots aren't moving across the surface. The surface itself is growing. And from any single dot's perspective, every other dot is moving away, with more distant dots receding faster. And this is what Friedman's math had predicted. This is what Lemaitre had proposed. The universe is expanding. It's not static. It never was. Einstein's cosmological constant, his careful fudge factor to keep the universe still, was unnecessary. When Einstein finally accepted this, after visiting Hubble at Mount Wilson in 1931 and seeing the evidence firsthand, he reportedly called the cosmological constant the biggest blunder of his career. Although, and this is a delicious twist we'll come back to later, it turns out the cosmological constant might not have been a blunder at all. But we'll get there. For now, think about what Hubble's discovery implies if you run the clock backward. If the universe is expanding, if galaxies are moving apart, then in the past, they must have been closer together. Go back far enough, and everything in the observable universe was squeezed into an unimaginably small, unimaginably dense, unimaginably hot state. A primordial fireball. A beginning. Lemaitre grasped this almost immediately. He called it the primeval atom, a single, ultra-dense quantum of energy from which everything emerged. It was a poetic name, and not quite right in the details, but the core idea was revolutionary. The universe had a beginning. It started from an incredibly compressed state and has been expanding and cooling ever since. Not everyone loved this idea. In fact, one of its most vocal critics gave it the name that stuck. In 1949, the British astronomer Fred Hoyle, a brilliant, combative, endlessly entertaining character who we'll spend more time with, was being interviewed on a BBC radio program and dismissively referred to Lemaitre's expanding from a beginning model as this Big Bang idea. He meant it as mockery. He preferred his own model, called the steady state theory, which proposed that the universe had no beginning and no end, that it was expanding, yes, but that new matter was continuously being created to fill in the gaps, so the universe always looked roughly the same on large scales, an eternal, self-renewing cosmos. And for about 15 years, the Big Bang and the steady state were genuine rivals. Both had serious physicists behind them. Both could explain the observed expansion. The question was whether there was any way to tell them apart, any observation that would favor one over the other. And it turned out there was. In fact, there were two. The first involved the lightest elements in the universe, hydrogen, helium, and tiny traces of lithium, and a remarkable calculation about what happens in the first few minutes after a universe is born. Here's the setup. If the Big Bang actually happened, if everything really was crushed together in this impossibly hot, impossibly dense state, then the early universe would have been like the inside of a star. Actually, much hotter than any star. We're talking temperatures in the billions of degrees within the first few seconds. And at those temperatures, you don't really have atoms. You don't even have stable atomic nuclei. You just have this screaming hot soup of protons, neutrons, electrons, photons, all slamming into each other at tremendous energies. A plasma, in the truest sense of the word. But here's what's clever. The universe is expanding, and as it expands, it cools. So there's this narrow window of time, starting maybe 10 seconds or so after the initial moment and lasting only until about 20 minutes in, where the temperature is just right. Hot enough for nuclear fusion to happen, but cool enough for the products of that fusion to survive without being immediately blasted apart. 20 minutes. That's it. That's all the universe gets. After that, the expansion has cooled things down too far for fusion to continue, and whatever mix of elements you've got at that point is basically what you're stuck with. So what gets built in those 20 minutes? Mostly helium. You start with roughly equal numbers of protons and neutrons. Well, not quite equal, because neutrons are slightly heavier than protons, and there's a slight preference for protons, so by the time nucleosynthesis kicks in, you've got about 7 protons for every neutron. Those neutrons almost all get swept up into helium-4 nuclei, which are incredibly stable. 2 protons, 2 neutrons bound together tightly. And when you run the numbers, you predict that the universe should come out of this era with roughly 75% hydrogen and 25% helium by mass, plus tiny trace amounts of deuterium. That's heavy hydrogen, helium-3, and lithium-7. Tiny, tiny amounts of lithium, almost nothing heavier. And this prediction is testable. You can go out and measure the actual abundances of these light elements in the universe, not in stars, where fusion has been cooking heavier elements for billions of years, but in pristine, unprocessed gas clouds, the most ancient and untouched material you can find. And when astronomers did exactly that, the match was remarkable. About 75% hydrogen, about 25% helium. The deuterium abundance, which is particularly sensitive to the density of ordinary matter in the early universe, matched beautifully. Even the lithium numbers were in the right ballpark, though lithium has always been a bit of a headache. The observed amount is a factor of a few lower than predicted, and cosmologists are still arguing about why. But the overall picture was stunning. The Big Bang model, with its specific predictions about what should have been cooked up in those first 20 minutes, nailed the composition of the universe. Now, the steady-state theory had no natural explanation for this. If the universe has always existed in roughly the same state, with new matter being created continuously, there's no reason to expect this particular ratio of hydrogen to helium. You'd have to invoke some other process, some other mechanism, and none of the proposals were convincing. So that was strike one against the steady state. But the second test, the one that really sealed the deal, involved something even more extraordinary. And to understand it, you need to think about what happens to all that light, all those photons trapped in the early universe. Go back to that hot, dense plasma in the first few 100,000 years after the Big Bang. The universe is filled with photons, light, but that light can't travel freely. It keeps running into electrons. Free electrons are everywhere, and photons scatter off them constantly, like trying to see through the densest fog you can imagine. The universe is opaque. Light takes a step, bounces off an electron, takes another step, bounces again. It's going nowhere. But the universe is still expanding, still cooling. And around 380,000 years after the Big Bang, which sounds like a long time, but cosmologically it's the blink of an eye, the temperature drops to about 3,000 degrees Kelvin. And at that temperature, something wonderful happens. Electrons slow down enough to be captured by protons and helium nuclei. They combine to form neutral atoms for the first time. Hydrogen atoms, helium atoms, just sitting there, electrically neutral. And neutral atoms are mostly transparent to photons. Suddenly, the fog lifts. The universe goes from opaque to transparent almost all at once, in a transition that cosmologists call recombination, which is a slightly misleading name since the electrons and nuclei had never been combined before, so it's really the first combination, not a recombination, but the name stuck, and nobody's going to change it now. So at that moment, 380,000 years in, all those photons that had been bouncing around, trapped in the plasma, are suddenly free. They stream out in every direction, and they've been traveling ever since, for 13.8 billion years. And here's the thing. They're still here. They're everywhere. They fill the entire universe, coming from every direction in the sky. But they've been stretched. Remember, the universe has been expanding all this time, and as space expands, it stretches the wavelength of light traveling through it. Those photons started out as visible light, roughly, the glow of a 3,000-degree surface, kind of an orange-red color. But after 13.8 billion years of expansion, their wavelengths have been stretched by a factor of about 1,100. They've been redshifted from visible light all the way down into the microwave part of the spectrum. They're now microwave radiation, with a temperature of just 2.725 degrees above absolute zero. Almost nothing. Just the faintest whisper of warmth. Everywhere you look. This is the cosmic microwave background, the CMB, and its existence was predicted before it was found. In the late 1940s, the physicist George Gamow and his colleagues Ralph Alpher and Robert Herman were working out the details of Big Bang nucleosynthesis. They were the ones who really put the numbers together on how the light elements would have been forged. And Alpher and Herman realized that if the early universe was this hot, dense plasma, then the radiation from that era should still be around, cooled by the expansion to just a few degrees above absolute zero. They published this prediction in 1948. The universe should be bathed in a faint glow of microwave radiation, uniform in every direction, a relic of the moment when the cosmos first became transparent. And then, almost nothing happened. The prediction kind of fell through the cracks. It wasn't that people rejected it. It was more that nobody quite realized it was detectable with existing technology, or perhaps nobody connected the theorists with the experimentalists who might have gone looking for it. It's one of those frustrating near misses in the history of science. The prediction was out there, in the literature, and it sat there for almost 2 decades. Until 1964, when 2 radio astronomers at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson, stumbled onto it completely by accident. They were calibrating a large horn antenna, originally built for satellite communication, and they kept picking up this persistent, low-level noise. A faint hiss of microwave radiation coming from everywhere in the sky, day and night, no matter which direction they pointed the antenna. They couldn't get rid of it. They checked everything. They thought it might be interference from New York City. They thought it might be caused by pigeons nesting in the antenna. And this is a real detail. They actually found pigeons roosting inside the horn and cleaned out what Penzias diplomatically called a white dielectric material, which is a physicist's way of saying pigeon droppings. They cleaned it all out, patched up the antenna, and the noise was still there. It was everywhere. It was uniform. It corresponded to a temperature of about 3.5 Kelvin, later refined to 2.725 Kelvin, and Penzias and Wilson had no idea what it was. Meanwhile, just 30 miles away at Princeton University, a group led by Robert Dicke and Jim Peebles had independently re-derived the prediction of this background radiation and were actually building an antenna to go look for it. They were so close to detecting it themselves. And then Penzias and Wilson heard about the Princeton group's work through a mutual contact, and the two teams connected. Penzias and Wilson had the observation. Dicke and Peebles had the explanation. They published companion papers in 1965, and when Dicke hung up the phone after learning about the Bell Lab's detection, he reportedly turned to his colleagues and said, "Well, boys, we've been scooped." That background radiation, that faint, uniform glow coming from every point in the sky, was the smoking gun. It was exactly what you'd expect if the universe had once been in a hot, dense state and had been expanding and cooling ever since. The steady-state theory had no explanation for it. None. You could try to argue that the microwaves were produced by some other source, starlight absorbed and re-emitted by dust maybe, but the spectrum was wrong for that. The CMB has what's called a perfect blackbody spectrum, which means it looks exactly like the radiation emitted by an object at a single uniform temperature. And when I say perfect, I mean perfect. Later measurements by the COBE satellite in 1990 showed that the CMB spectrum matches a theoretical blackbody curve more precisely than any other measurement in the history of physics. The error bars are smaller than the thickness of the line on the graph. When John Mather presented this result at an astronomy conference, the audience burst into spontaneous applause. And that almost never happens at physics talks. So by the mid-1960s, the Big Bang had won. The steady-state theory didn't disappear overnight. Hoyle continued to defend and modify it for decades, because that's the kind of person he was, stubborn and brilliant in equal measure. But the scientific consensus shifted decisively. The universe had a beginning. It started hot and dense, it expanded and cooled, and the evidence was written across the sky in microwave light that had been traveling for over 13 billion years. But here's what's interesting. Winning the argument, proving that the Big Bang happened, immediately raised a whole new set of questions, because when you looked at that cosmic microwave background carefully, it was almost too perfect, too smooth, too uniform. The temperature was the same in every direction to 1 part in 100,000. Think about what that means. You point your antenna at one patch of sky and you measure 2.7250 Kelvin. You point it at the exact opposite side of the sky, at light that has traveled to you from a region of the universe that is, today, tens of billions of light years away from the first region. And you measure 2.7250 Kelvin. The same temperature, to extraordinary precision. And that's a problem, because those two regions of the sky, on opposite sides of your view, have never been in contact with each other. Light hasn't had time to travel between them since the beginning of the universe. There's been no way for them to exchange energy, to equilibrate, to agree on a temperature. And yet they're at the same temperature. It's as if you opened two thermoses on opposite sides of the Earth and found the coffee inside both at exactly the same temperature, down to 1,000th of a degree, even though nobody had coordinated anything. How? How is the universe so uniform when there's been no physical mechanism to make it uniform? This is called the horizon problem, and it was one of several deep puzzles about the Big Bang that emerged in the 1970s. Another was the flatness problem, the observation that the geometry of the universe appears to be almost perfectly flat, like a tabletop rather than curved like a sphere or a saddle, and that this flatness requires the density of the universe at very early times to have been tuned to an almost absurdly precise value. We're talking about the density being equal to the critical density to 1 part in 10 to the 60th power in the first fraction of a second. That's not a number that makes you comfortable. That's a number that makes you think you're missing something. And in 1979, a young physicist at Stanford named Alan Guth was thinking about a completely different problem. A problem from particle physics involving magnetic monopoles. These hypothetical particles that should have been produced in enormous quantities in the early universe but have never been observed. When he stumbled onto an idea that would solve all of these puzzles at once. He stayed up late one night, working through the math, and when he realized what he had, he wrote in his notebook, in capital letters, the words "spectacular realization." And then, underneath, he wrote the idea that would reshape our understanding of the first moments of the universe. The idea was inflation. And inflation, at its core, is beautifully simple to state, even though the physics underneath it is anything but. What Guth proposed was this. In the very first sliver of a second after the Big Bang, we're talking about a time interval so small it makes a nanosecond look like an eternity, something like 10 to the minus 36th of a second after the beginning. The universe underwent a brief, violent, exponential expansion, not the kind of steady expansion Hubble had measured, where galaxies drift apart over billions of years. No. This was a moment when the fabric of space itself stretched by a factor of at least 10 to the 26th in a tiny fraction of a second. To put that in perspective, imagine taking something smaller than a proton and blowing it up to something larger than the entire observable universe today. That's the kind of expansion we're talking about. And then, just as suddenly as it started, it stopped. The universe settled back into the more leisurely expansion that Hubble would eventually observe, and the rest of cosmic history unfolded from there. Now, you might be thinking, that sounds completely insane. And honestly, it kind of does. But here's the thing. It works. It solves the problems. Let's go back to the horizon problem. That maddening puzzle about why the cosmic microwave background looks the same temperature in every direction, even though opposite sides of the sky should never have been in contact with each other. Inflation fixes this in the most elegant way imaginable. Before inflation happened, the universe was unimaginably tiny. So tiny that everything in it, all the stuff that would eventually become the entire observable universe, was crammed into a region small enough that light could easily cross it. Everything was in thermal contact. Everything had time to reach the same temperature, the same density, the same equilibrium. It was like one tiny room where the air had plenty of time to mix. And then inflation hit, and that tiny, perfectly uniform patch got stretched to cosmic scales in an instant. The uniformity was already there. Inflation just made it enormous. The reason the CMB looks the same in every direction isn't some mysterious coincidence. It's because everything we can see today originated from the same tiny, well-mixed region, blown up to absurd proportions. And the flatness problem? Same trick. Remember, the issue was that the universe's density had to be fine-tuned to an almost impossibly precise value early on, or else the universe would have either collapsed back on itself or flown apart so fast that no structures could ever form. The density had to equal the critical density to 1 part in 10 to the 60th power. That kind of fine-tuning screams that something deeper is going on, and inflation provides the answer. Think of it this way. Imagine you're standing on a basketball. You can see the curvature of the surface pretty clearly. It's obviously round. But now imagine that basketball suddenly inflates to the size of the Earth. You're still standing on it, but now the surface beneath your feet looks completely flat. You can't detect the curvature anymore because your little patch of the surface has been stretched so enormously that any curvature has been diluted to essentially zero. That's exactly what inflation does to the geometry of the universe. whatever curvature existed before inflation, and there could have been quite a lot, gets stretched out so dramatically that the observable universe afterward is indistinguishable from flat. You don't need fine-tuning. You just need inflation to do its thing, and flatness comes out naturally. And the monopole problem, the one Guth was actually trying to solve in the first place, inflation handles that too. Those magnetic monopoles that particle physics predicted should have been created in vast quantities in the hot early universe. Inflation dilutes them. If inflation happens after the monopoles are produced, the exponential expansion spreads them out across such an enormous volume that the chance of finding even one in our observable universe becomes essentially zero. They might exist somewhere, scattered across a universe far larger than what we can see, but we'd never encounter one. Problem solved. So Guth published his paper in 1981, and the response was electric. Physicists immediately recognized that inflation was potentially a huge deal. But, and this is important, Guth's original version had a problem. A pretty serious one, actually. In his model, inflation was driven by a quantum field stuck in what's called a false vacuum state. You can think of a false vacuum like a ball sitting in a shallow dip on a hillside. It's not at the bottom of the hill. That would be the true vacuum, the lowest energy state. But it's in a little depression, temporarily stuck. Eventually, the ball quantum tunnels through the barrier and rolls down to the true bottom, releasing energy as it goes. In Guth's picture, this transition from false vacuum to true vacuum is what ends inflation. The problem was that this transition didn't happen everywhere at once. It happened in random bubbles. Little patches of space would tunnel to the true vacuum and start expanding. But the space between the bubbles was still inflating exponentially, pushing the bubbles apart faster than they could merge. You'd end up with a universe that was incredibly lumpy and inhomogeneous, the exact opposite of what we observe. Guth himself recognized this flaw. He called it the graceful exit problem. Inflation was a spectacular idea that didn't quite know how to stop gracefully. And this is where André Linde comes in, and independently, Andreas Albrecht and Paul Steinhardt. In 1982, within about a year of Guth's original paper, they proposed what's called new inflation, or slow-roll inflation. Instead of the field being stuck in a false vacuum and tunneling out, they imagined a field, called the inflaton field, slowly rolling down a very gentle slope. Picture a ball on an almost flat hilltop, barely tilted. The ball rolls, but so slowly that the energy stored in the field remains nearly constant for a while, driving exponential expansion. Then, as the field reaches the steeper part of the slope and rolls down to the bottom, inflation ends smoothly everywhere, all at once. No bubbles, no graceful exit problem. The energy stored in the inflaton field gets converted into a hot soup of particles, reheating it's called, and from that point on, you get the standard hot Big Bang. So inflation doesn't replace the Big Bang. It's a prelude to it, a tiny fraction of a second of exponential stretching, followed by reheating, followed by everything we've already talked about: nucleosynthesis, the formation of light elements, the release of the CMB, all of it. Now, here's what's really clever, and this is the part that elevates inflation from a nice idea to something with genuine predictive power. Quantum mechanics tells us that even empty space isn't truly empty. There are tiny quantum fluctuations happening everywhere, all the time, little random jitters in the energy of every field. During inflation, these fluctuations got stretched along with everything else. A fluctuation that started at a subatomic scale got blown up to astronomical scales. And because inflation ended at slightly different times in slightly different places, because of these random quantum jitters, some regions of the universe ended up very slightly denser than others. We're talking about variations of about 1 part in 100,000. Tiny, almost nothing. But those tiny density variations are the seeds of everything. The slightly denser regions had slightly more gravitational pull, attracting more matter over time, growing denser still, eventually collapsing into the first galaxies, the first stars, the first clusters. The pattern of those initial fluctuations, their statistical properties, how their amplitude varies with scale, is something inflation makes specific predictions about. And those predictions can be tested. This is where the story connects back to the cosmic microwave background, that ancient light we talked about, the one Penzias and Wilson stumbled onto with their horn antenna in New Jersey. Remember how COBE confirmed that the CMB had a perfect blackbody spectrum? Well, COBE also did something else. In 1992, the COBE team, led by George Smoot, announced that they had detected tiny temperature variations in the CMB. Anisotropies, they're called. Fluctuations of about 1 part in 100,000. Exactly the kind of fluctuations that inflation predicted. These weren't noise. These were the fingerprints of quantum fluctuations from the first fraction of a second, stretched across the sky, frozen into the oldest light in the universe. Stephen Hawking called it the greatest discovery of the century, if not of all time. That might be a bit dramatic, but the point stands. We were looking at the quantum origins of cosmic structure written in microwave light, and then came the missions that sharpened the picture to breathtaking precision. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, which mapped the CMB fluctuations with far greater resolution than COBE. And then, in 2009, the European Space Agency launched Planck, which pushed the precision even further. The maps from these missions are staggering. They show the entire sky painted in tiny temperature variations, hot spots and cold spots, and the statistical pattern of those variations matches the predictions of inflationary theory with extraordinary accuracy. The spectrum of fluctuations is nearly scale invariant, meaning fluctuations at large scales have almost the same amplitude as fluctuations at small scales, with a very slight tilt. Exactly what slow-roll inflation predicts. The fluctuations are Gaussian, randomly distributed in a very specific statistical way. Again, just as inflation predicts. It's not proof in the mathematical sense. Science doesn't work that way. But it's the kind of agreement between theory and observation that makes you sit up and pay attention. And yet, even as inflation was being confirmed in these remarkable ways, the late 1990s brought a discovery that nobody saw coming, something that shook cosmology to its foundations and brought back a concept that Einstein had introduced and then abandoned decades earlier. In 1998, 2 independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were trying to measure something that seemed straightforward. They wanted to figure out how fast the expansion of the universe was slowing down. Because of course it should be slowing down, right? Gravity pulls matter together. The mutual gravitational attraction of everything in the universe should be acting like a brake on the expansion, gradually decelerating it over time. The question wasn't whether the expansion was decelerating, everyone assumed it was. The question was how quickly. And to measure that, they used a particular kind of exploding star called a Type 1a supernova, which is useful because these explosions all reach roughly the same peak brightness, making them excellent cosmic distance markers. You measure how bright a Type 1a supernova appears, you compare it to how bright you know it actually is, and the difference tells you how far away it is. You combine that with its redshift, and you can map out the expansion history of the universe over billions of years. Both teams did this. Both teams expected to find deceleration, and both teams found the opposite. The expansion of the universe isn't slowing down, it's speeding up. The universe is accelerating. And when they checked their results and rechecked them and had other people check them, the answer kept coming back the same. Some mysterious energy permeating all of space, is pushing the universe apart faster and faster. And the name we've given to this something, this energy we don't really understand, is dark energy. Dark energy. It's one of those names that sounds like it belongs in a science fiction movie. And honestly, the reality isn't that far from science fiction in terms of how strange it is. The term was coined around 1998 by the cosmologist Michael Turner at the University of Chicago, and it stuck because, well, we needed to call it something. We had discovered that roughly 68% of the total energy content of the universe is made up of this stuff, and we had almost no idea what it actually is. And here's the humbling part. We still don't. Not really. Dark energy is one of the biggest open questions in all of physics, and it's been that way for over a quarter century now. But let's slow down and think about what the discovery actually means, because it's genuinely one of the most startling things human beings have ever figured out about the universe they live in. You've got a cosmos that started with this tremendous expansion, the Big Bang, and for billions of years, gravity has been working to slow that expansion down. Every galaxy pulling on every other galaxy, every bit of matter tugging on every other bit of matter. And for a long time, that's exactly what was happening. The expansion was decelerating, just like you'd expect. But then, somewhere around 5 or 6 billion years ago, something changed. The expansion stopped slowing down and started speeding up. It's as if you threw a ball into the air, watched it rise and begin to slow, and then instead of coming back down, it suddenly accelerated upward, faster and faster, shooting off into the sky. That would be deeply weird, right? You'd want to know what force was pushing it. That's the situation we're in with the universe. Now, here's where Einstein's old cosmological constant comes back into the story, and it's almost poetic how it happens. Remember, back in 1917, Einstein added a term to his field equations, the cosmological constant, lambda, because he wanted the universe to be static, and without it, his equations predicted either expansion or contraction. When Hubble showed the universe was expanding, Einstein dropped the constant, reportedly calling it his greatest blunder. But mathematically, the cosmological constant never went away. It was always sitting there in the equations as a possibility. And what the 1998 supernova results suggested was that something very much like a cosmological constant was real. Not because the universe is static, it obviously isn't, but because there's an energy associated with empty space itself, a kind of intrinsic energy density of the vacuum, and that energy acts as a repulsive force, pushing space apart. Think about that for a second. Empty space, space with nothing in it, no particles, no radiation, no matter, has energy. And that energy has a gravitational effect, but instead of pulling things together like normal matter and energy do, it pushes things apart. In general relativity, it turns out that pressure contributes to gravity, not just mass and energy. And the cosmological constant produces a negative pressure, a kind of tension in the fabric of space, and that negative pressure drives accelerated expansion. The more space you have, the more dark energy you have, because it's a property of space itself. So as the universe expands and creates more space, there's more dark energy, which drives more expansion, which creates more space, which creates more dark energy. It's a runaway process, and it means the expansion will just keep accelerating forever, as far as we can tell. And this is where things get a little melancholy if you're the kind of person who finds cosmology emotionally resonant. Because accelerating expansion means that galaxies that are far away from us are receding faster and faster. And eventually, not tomorrow, not in 1,000,000 years, but in tens of billions of years, distant galaxies will be moving away from us faster than the speed of light. Now, that sounds like it should be impossible, right? Nothing can travel faster than light. But that's a rule about objects moving through space. Space itself can expand at any rate it likes. There's no speed limit on the stretching of the fabric of the cosmos. And when a galaxy recedes faster than light, its light can never reach us. It crosses a kind of cosmic horizon and disappears from our observable universe forever. So if you imagine astronomers in the very distant future, trillions of years from now, assuming there are any, they would look out at the sky and see nothing. No other galaxies, no cosmic microwave background, no evidence of the Big Bang at all. The observable universe would have shrunk to just their own local group of gravitationally bound galaxies, and everything else would have been carried beyond the horizon by the relentless expansion. They would have no way of knowing that the universe was once filled with billions of galaxies, no way of detecting the faint afterglow of creation. The evidence would simply be gone. Which raises a haunting question. Are we in that situation now? Is there evidence of something fundamental about the cosmos that has already been carried beyond our horizon? Something we'll never be able to see? We don't know. We can't know. And that's a strange thing to sit with. But anyway, let's come back to dark energy itself, because there's a real puzzle here that physicists have been wrestling with for decades, and it's called the cosmological constant problem. And some people have called it the worst prediction in the history of physics. Here's the issue. Quantum field theory, the framework that describes particle physics, predicts that the vacuum of space should have energy. Empty space is never truly empty. It's full of quantum fluctuations, virtual particles popping in and out of existence. And when you calculate how much energy all those fluctuations should contribute to the vacuum, you get a number. And then, when you look at the actual observed value of dark energy, the value that matches the accelerating expansion, you get a different number. And the difference between those two numbers is not small. The quantum field theory prediction is larger than the observed value by a factor of about 10 to the power of 120. That's a 1 followed by 120 zeros. It is, by a spectacular margin, the worst disagreement between theory and observation in the entire history of science. Now, you might think, well, maybe the calculation is just wrong. And that's possible. But the calculation follows straightforwardly from well-established physics, and nobody has figured out a convincing reason why it should give a different answer. Some physicists think there must be some unknown symmetry or mechanism that cancels out most of that vacuum energy, bringing it down to the tiny value we observe. But nobody has found that mechanism. Others have suggested that maybe the cosmological constant is exactly zero, that the cancellation is perfect, and dark energy is actually something else entirely, some new field that permeates space. This hypothetical field is sometimes called quintessence, borrowing a term from ancient philosophy for the fifth element. Quintessence would be different from a cosmological constant because its energy density could change over time, whereas a true cosmological constant is, well, constant. And there are observations that could potentially distinguish between these possibilities, measurements of how the expansion rate has changed over cosmic history, and so far the data is consistent with a plain cosmological constant. But the error bars are still large enough that quintessence isn't ruled out. And then there's an even stranger possibility, one that makes some physicists deeply uncomfortable and others find compelling. It's called the anthropic explanation, and it goes something like this. Maybe the value of the cosmological constant isn't determined by any fundamental physical principle. Maybe it's different in different regions of an unimaginably vast multiverse, and we happen to live in a region where the value is small enough to allow galaxies and stars and planets and people to form. If the cosmological constant were much larger, dark energy would have torn the universe apart before any structures could form. If it were negative and large, the universe would have collapsed. Only in the narrow range where it's small and positive can observers like us exist to measure it. This is a deeply controversial idea because it feels like giving up on finding a real explanation. It's not a prediction. It's a selection effect. But some versions of string theory, which we won't dive too deep into tonight, do predict a vast landscape of possible universes with different values of fundamental constants. And in that context, the anthropic argument has a certain logic to it. Whether it's satisfying is another question entirely. Let's step back for a moment, because we've covered a lot of ground tonight, and I want to paint the big picture of what we've actually figured out. We've arrived at what cosmologists call the concordance model, or the lambda CDM model, where lambda stands for the cosmological constant, dark energy, and CDM stands for cold, dark matter. This is the standard model of cosmology, and it fits an extraordinary range of observations. The cosmic microwave background, the large-scale distribution of galaxies, the abundance of light elements, the accelerating expansion, the age of the universe, about 13.8 billion years, the geometry of space, flat or very nearly so, the composition of the universe, roughly 68% dark energy, 27% dark matter, and only about 5% ordinary matter. 5%. Everything you've ever seen, touched, tasted, smelled, every star, every planet, every person, every atom in your body, makes up about 5% of what's out there. The rest is dark. Dark matter, which we've detected through its gravitational effects on galaxies and galaxy clusters, and the cosmic microwave background, but which we've never directly captured in a laboratory, and dark energy, which we've inferred from the accelerating expansion, but whose fundamental nature remains a complete mystery. Think about what that means. We've built this remarkably precise model of the universe. We can predict the temperature of the cosmic microwave background to 6 decimal places. We can calculate the ratio of hydrogen to helium produced in the first few minutes after the Big Bang, and it matches what we observe. We can trace the growth of cosmic structure from tiny quantum fluctuations during inflation to the vast web of galaxy clusters we see today. The model works. It works astonishingly well. And yet 95% of the universe is made of stuff we don't understand. That's not a failure. It's a signpost. It's telling us that there are deep things about nature that we haven't figured out yet, and that the next great revolution in physics is probably hiding in that 95%. And you know what? That's actually a beautiful place to be. Because the history we've walked through tonight, from those Babylonian astronomers scratching records of planetary motions into clay tablets, to Copernicus quietly rearranging the solar system, to Newton unifying the falling apple and the orbiting moon, to Einstein reimagining space and time as a single dynamic fabric, to Lemaitre proposing that everything began from a primeval atom, to Penzias and Wilson hearing the echo of creation in their antenna, to Guth imagining a universe that inflated from almost nothing in a fraction of a second. That whole story is a story of people staring at the sky and refusing to stop asking questions. Every generation thought they were close to the final answer, and every generation turned out to be wrong in some beautiful, productive way that opened up the next chapter. And the questions that are open right now are some of the best questions we've ever had. What is dark energy? What is dark matter? What happened at the very first instant of the Big Bang, before inflation, if there even was a before? Is our universe one of many? Are there dimensions of space we can't perceive? What is the ultimate fate of everything? These aren't small questions. These are the kinds of questions that keep physicists awake at night. Though tonight, they don't need to keep you awake. Because here's the thing about the universe, and maybe this is the gentlest thought to drift off with. It's been here for 13.8 billion years. It's not going anywhere tonight. The cosmic microwave background is washing over you right now, this very moment, a faint whisper of photons that have been traveling since the universe was 380,000 years old, and they're passing through the walls of your room, through you, through everything, at the speed of light, carrying information about the earliest moments of creation. You can't feel them. You can't see them. But they're there. They've always been there for your entire life, for your parents' lives, for the entire history of the human species. And we only noticed them in 1964, by accident, because two engineers in New Jersey couldn't get rid of a hum in their antenna. The universe is patient. It doesn't mind if you fall asleep before the story is finished. It'll still be expanding when you wake up, a little bit faster than it was when you closed your eyes. Every galaxy a tiny bit farther from every other galaxy. The cosmic web stretching and thinning. The background radiation cooling by an imperceptible fraction of a degree. And somewhere, right now, someone is sitting in front of a computer screen, or standing at a whiteboard, or lying in bed just like you, turning one of these unsolved puzzles over in their mind. And maybe they're about to have the kind of idea that changes everything. The kind of idea that Friedman had, or Lemaitre had, or Einstein had on his best days. The kind of idea that makes the next generation look back and say, oh, that's what we were missing. But that's a story for another night. For now, the universe is here, and it's vast, and it's strange, and it's more beautiful than anyone in the history of our species ever had reason to expect. And you're part of it. Every atom in your body was forged in the heart of a star, or in the first few minutes after the Big Bang. You are, quite literally, the universe thinking about itself, wondering where it came from, wondering where it's going. And that's enough. That's more than enough. Let that thought settle. Let it get comfortable. And let the rest of the questions wait until morning. They'll still be there. They've got nowhere else to be.